In this work, we present EmoFace, a novel audio-driven methodology for creating facial animations with vivid emotional dynamics. Here is the outline of today's talk. First, I will talk about the motivation of this work. In virtual reality, avatars can be generated by vision-based methods like face tracking, which have highly realistic outcomes. But when the user wears a headset, we are unable to capture facial expressions. Under such circumstances, employing audio input as the foundation for generating avatars becomes a more suitable approach. Some previous works focus on audio-driven facial animations, such as MEAD and EVP. However, they mainly focus on outputting realistic videos by editing a reference image. So they cannot be directly applied to 3D facial models driven by a sequence of parameters. What's more, the naturalness of their generated faces is not sufficient. There are some latest works that applied transformer structure in the process, like FaceFormer and EmoTalk. The output of these models are parameters for driving 3D facial models, such as facial meshes or blend shapes, which are similar to our target. Compared with previous works, they can generate better lip synchronization with the input audio. However, the upper face is ignored, making the generated face look stiff. As for audiovisual datasets, there are a few datasets frequently used in previous works. MEAD is a large audiovisual dataset that contains multiple emotions, intensities, and characters. But it contains captured videos only. Dataset and Ravdis contain audio and its corresponding facial meshes. However, the problem is our 3D model cannot be driven by meshes, and dataset does not consider different emotions. To address this issue, we proposed a new AudioRig dataset recorded in Chinese. It contains 847 clips for 7 emotions in total. Each emotion contains 2 types of sentences: special sentences that appear only once in this emotion, common sentences that appear in every emotion. After capturing videos, they are processed to extract corresponding metahuman controller values for each frame. Here is an example of processed data.
此外，成本因素也成为支撑钢价的原因之一。
We further evaluate the extracted controller values and phonemes of the dataset. The image on the left shows that there is a strong symmetry between the left and right sides of the face. The distribution figure on the right indicates our dataset covers all phonemes in Chinese. Here is the overview of our system. We implement audio encoder and emotion encoder to capture their features separately, and then map the combined feature to target emotional rig parameters through an audio 2 rig module. The audio encoder is based on Wave 2 Vec2 and initialized with pre-trained Wave 2 Vec2 base 960H model. Compared with traditional MFCC spectrogram, it can better extract audio features. When training, the weights of the feature extractor are frozen. As for emotion encoder, it produces emotion features given the target emotion label. The design of emotion encoder allows free control of the desired emotional face. It further allows the possibility of mixing emotions and having different emotions for each part of the animation. After combining audio feature and emotion feature, Audio 2 Rig module maps them into a sequence of controller values. Unlike previous works that apply transformer decoder for mapping, our model is based on transformer encoder layer. Our choice is mainly due to 3 considerations. First, the inference time of encoder layer is much faster than decoder layers. Second, only a few previous frames offer insight for forecasting the next frame. And contextual information is already contained in the extracted features. Third, we apply a Savitsky-Golay filter to avoid possible jitter caused by direct mapping. Although the model can already generate expressions with accurate emotion and lip movements, the upper face is still neglected. We address this issue by adding blink and gaze in the generated animation. As blinks are not much related to the audio input, we generate blinks at a certain frequency. We collect data by detecting blinks in MEAD dataset, which are highly related to eye aspect ratio. The EAR value can be calculated by 6 landmarks of the eye. EAR represents the level of openness, and a low value indicates a state of eye closed. One traditional way of detecting blinks is to set a threshold. Once there are consecutive values lower than the threshold, there is a blink. But it is hard to choose the exact threshold suitable for all people. So we trained a SVM predictor to detect blinks by neighboring 7 frames, which avoids detecting false blinks. We can see the frequency is log norm. We could sample blink intervals and add blinks. As for eye gaze, we add some random eye movements to make the expression less dull. For each cycle, 3 parameters are sampled: the angle to look at, the extent of eyeball movement, and the length of interval. There is a possibility of returning to the center point to balance the frequency of eye rolls. Here are the results for 7 emotions generated by our model, compared with ground truth.
那一副无所谓的模样，让人气愤得很。城里姑娘嘛，都是有一点儿的，自然长得牛头马面，一看就叫人害怕。既要维护养殖户，又要维持市场稳定。你的身影总是在我心里晃来晃去。哎呀，这简直就是给我雪上加霜！哇塞，这是什么东西啊？
We further conduct a comparison to the state-of-the-art methods, including FaceFormer and EmoTalk. The difference is that FaceFormer does not consider emotions. EmoTalk disentangles content and emotion directly from the input audio rather than input emotion label. And the datasets used for training are different for all 3 models. For better comparison, we adjusted the input labels and output dimensions of them and trained in our dataset. Here is the comparison of result between 3 methods.
最可惜的是，他莫名其妙的就成了最后的赢家。
We conducted quantitative and qualitative analyses of the results. They indicate that our method could achieve the best result among them. We further designed a user study. The result on emotion recognition shows that EmoTalk achieves the worst score. This is expected because it directly predicts emotion from audio input, and any wrong prediction can affect the result. We also find that ground truth, EmoFace, and FaceFormer achieve similar results, which proves that our model can express emotions well. In terms of naturalness, our results show that EmoFace significantly surpasses the other 2. It is probably because we added blink and gaze to make the animation less dull. It shows that our method can produce more natural facial expressions than the other 2 models. As for lip synchronization, all 3 models achieve good results. This can be related to pre-trained Wave 2 VEC2 audio feature extractor in all 3 models. In comparison, FaceFormer lags for its insufficient lip movements. This demonstrates that our model could produce more precise lip movements. However, there are still some problems with our method. First, we do not solve the problem of multiple mappings between audio and facial expressions. Second, our model is based on a large pre-trained model, which can lead to high inference costs. Third, our dataset has a relatively small scale. Lastly, the generated expressions lack emotional intensity and facial details. In this work, we construct a dataset recorded in Chinese with multiple emotions. We also propose a model for audio-driven multi-emotional facial generation. To enhance the naturalness of generated animation, we additionally introduce blink and gaze. We evaluate our model with further analysis and user study, which indicate that our model excels at conveying emotions and generating natural facial expressions with good lip synchronization. Thank you very much for listening.